With drones playing a more significant role in our society, the importance of the drone's environmental awareness intensifies. ELUDE is a prototype to help drones become more aware. By detecting and evading obstacles in the flight path, drones would be one step closer to fully independent flight. So what is ELUDE? ELUDE is a navigational system that allows a quadcopter to follow through a predetermined set of waypoints while taking evasive maneuvers to avoid incoming projectiles.
Our project is meant to be a proof of concept for the potential of robotic environmental awareness. It was specifically designed for competition against another senior design team, Team Targeting. The competition involves us navigating through 3 waypoints on a 30 by 40 yard field, while Team Targeting fires Nerf dart projectiles at us from a known source. We designed our system on an AR Drone 2.0 quadcopter, and specifically make use of the built-in forward-facing camera, downward-facing camera, and open-source navigational software.
The detection component is designed to identify incoming projectiles and approximate their trajectory. Our system relies on some simplifying assumptions about the projectiles. The system can detect Nerf darts of particular dimensions with an orange and blue color scheme. Detection is achieved visually through the front-facing camera. An HSV color filter is applied to the image to isolate the orange and blue colors of the dart. A smallest fit rectangle is then placed around the dart. The dimensions of this rectangle are used to estimate a position and location for the incoming dart. Several measurements are taken over several frames, and the data is extrapolated to get a trajectory for the dart. We are then able to see whether it is coming straight at us, barely missing, or moving completely perpendicular. The estimated dart trajectory is passed to the evasion system to analyze.
Given a series of location points from the detection node, the evasion node must determine the optimal evasive maneuver to perform to get out of the path of the dart. This is done by first creating a linear regression line on the data given to us from the detection node. Once the line is created, it is compared with the current location of the quadcopter to determine if it will pass within a certain threshold, currently set at 2 feet, of the quadcopter. If the dart is determined to pass within a certain threshold of the quadcopter, evasion is determined to be necessary. If evasion is necessary, we look at our pool of evasive maneuvers currently forward, backwards, left, and right, and determine the optimal maneuver which will remove us from the path of the dart in the least amount of time.
Robotic systems use external landmarks to identify a space and correct internal sensor error. When not viewing a landmark, a quadcopter relies on its onboard sensors to predict its motion through space. However, their sensors are not 100% accurate, so the longer a quadcopter goes without seeing a landmark, the worse its predicted location becomes. For our system, we made use of a series of landmarks called April tags. Each tag is unique from every other tag in the library, so by hard-coding a set tag to a known location on the playing field, our quadcopter can know exactly where it is on the field when viewing any tag.
The controller controls the quadcopter by sending a velocity vector to the drone's driver. A PID controller is used to calculate these velocities from the current location and the target. Once the drone reaches its current target, the controller begins navigating to the next target. After the drone has navigated through all of its waypoints, the controller will land the drone. While the controller is driving the drone, it is also handling any service requests from the evasion node. Whenever the controller receives an evasion request, the controller forwards this request to the drone to perform one of the evasive animations in our limited selection of animations.
The final result of our work on ELUDE is a quadcopter system which is aware of its location, can navigate to waypoints, sense incoming projectiles, and take evasive action as necessary.
This project would not have been possible without the help of the NIMS Lab, Innovation Labs, University of Nebraska-Lincoln, and their computer science department.